So let's have a look at, in particular, motion, basically. So applying the calculus to the physical world. So some terminology, we've talked about displacement. In maths, a lot of the time we just use the pronumeral x because we imagine straight line motion and we're just travelling along the x-axis. It doesn't have to be x, of course. I mean, it could be y. I think in physics they use s, don't they, a lot for displacement. So is distance, but with direction. So the positive and the negative tells you in which direction. And so that's one of the advantages of just looking at straight line motion, because either you're going forwards or you're going backwards. You're going positive direction or negative direction. Velocity, well then we've got several ways we could write it. Obviously v for velocity, but now we're talking about rates of change, we could write it as dx to t. Or we could use the dot notation. This is the notation that Newton used when he first came up with the idea, and it was specifically for motion. So you don't normally write x dot to mean derivative, you write x dot to mean velocity. Okay, so we really just keep that for motion, the x dot notation. And so it's the rate of change of displacement with respect to time. So it could be thought of as speed, but with direction. So positive means we're going one way, negative means we're going in the other direction. Which then brings us to acceleration. And so now we have even more notations we could use. A is an obvious one, but it's the rate of change of velocity with respect to time. So we could say dv to t, but that also means it's the second derivative of displacement. So we could write it that way, which then using the dot notation means we could write x double dot for acceleration, or we could just use v with a single dot. So they're all different ways we could write acceleration. Now, here's the thing. Velocity, speed with direction. Acceleration is one of those weird ones because we use the same word for both. So acceleration is acceleration with direction. I know, it doesn't make sense, does it? But one thing to point out, and here it is in the note there, this thing called deceleration, or slowing down if you like. There really is no such thing as deceleration. What it is you're accelerating in the opposite direction to which you're travelling. So if you're accelerating in the opposite direction, it's like someone's grabbing you on the shirt and pulling you back, so you slow down. So yeah, people use the word deceleration, but that's actually what it is. Acceleration in the opposite direction to the velocity. Whoops, all right, here's a displacement time graph. So now we build on our travel graphs even more, because we can have negatives. So you can see I've now got part of the curve below the axis, part of the curve above the axis. But it's still a travel graph, if you like. I can draw the tangent in. Remember the tangent, the slope of that tangent will give us the instantaneous velocity at that point. Now, I can now draw a velocity time graph. All I'm really doing is drawing a graph of the derivative, and I can point out key features. Things like that turning point at t equals 1. Well, I know that's when the derivative equals 0, so therefore it must cut the axis on the velocity graph, and things like that. And we'll talk a bit more about that later. And so here you could work out instantaneous acceleration, similar to what we did with the displacement time graph, but now we do it with the velocity time graph. So if we want to know acceleration at a particular instant, it would be the slope of the tangent at that point. And then we could draw an acceleration graph. And whoop, there it is. Now think about this with functions. That first one there, the displacement time graph, I mean, it looks like a cubic. So there's no surprise then that the velocity time graph is a quadratic. Differentiate a cubic, you get a quadratic. Differentiate a quadratic, what do you get? You get a linear function, and there's our acceleration graph. It is indeed a linear function. So distance travelled would be 7 metres. Remember they're saying distance, not displacement. So I've gone up 2, then down 4, up another 1, so all up travelled 7 metres. Whereas displacement, how far have I travelled from where I started with, would be -1. We've moved 1 metre, but in the negative direction. Average speed. So speed is distance over time. So it would be that distance we travelled 7 over the time 4. Average velocity, displacement over time. So that would be minus a quarter. Displacement x from the origin, time t seconds, and we happen to know the equation for our travel graph. It's x equals t cubed minus 21 t squared. Now the beauty of knowing about calculus is we don't necessarily have to draw the graph now. We can just use the ideas from calculus to solve problems. So if I want to find the acceleration, I want a formula for acceleration time t. Well, all it's really asking me to do is differentiate this twice. Simple enough, it's a polynomial. So velocity 3t squared minus 42t, acceleration 6t minus 42. Find the times when the particle is stationary, and that's where the language of the calculus is nice. Stationary points, when the particle is stationary. It's all the same thing. Velocity equals 0. Well, that makes sense. Velocity equals 0, you're stationary. So we solve that. But when you're writing your solution out, remember, your solution is not a solution for you, it's a solution for someone else. They want to know why you're solving this equation. So you tell them why. You want to know when the particle's stationary? I know it's stationary when the velocity is equal to 0. So I know if I solve this, I will get the answer. And the two answers are 0 and 14. And if I want to answer it really fancily, I'll put that in a word sentence. Particle is stationary initially, that's t equals 0 by the way, and again after 14 seconds. This time we know it's moving on the x-axis, starts at rest, t equals 0, but it's actually starting not at the origin, it's starting at x equals 7. So its acceleration is 2 plus 6t. We want to find out where it is when t equals 3. Okay. We know acceleration is 2 plus 6t. So now we use integration. We want to go back the other way. So if I integrate that, and this is where constant becomes really important. We've got to work out what the constant is. When t equals 0, v equals 0. I would have got lucky if I forgot the constant because it turns out the constant's 0. So that would have been okay. But you can't always be that lucky. Let's get the displacement one. T squared plus t cubed plus a constant, but in this case, when t equals 0, x is 7. So actually the constant is 7. So had I forgot my constant, obviously I'm going to end up with the wrong answer here. So there's my equation. We want to know the position when t equals 3. So we sub in and we get 43. So I know after 3 seconds the particle is 43 units to the right of the origin. Or if you prefer, in the positive direction, or however you want to phrase it. Now, of course, that's how mere mortals would solve it. There's a much more efficient way of doing it. So that way I don't have to worry about the constant. I do it by using definite integrals rather than indefinite integrals. Instead of calling acceleration A, I'm calling it dv dt. Because what I can then do is what's called separating the variables. And we will see this a lot of this later when we look at differential equations. So I turn it into an integration problem, but then I make it a definite integral by matching up the conditions they've told me. Notice at the bottom of the integral, I put t is 0. So on the bottom of the velocity one, what was the velocity? Velocity was 0, so I put 0 there. I want to find something that links v and t, so they're the pronumerals I put at the top. And I just do these two simple integrations. Now when I'm going from 0 to v, I know the answer's got to be v. So I can jump straight to that one. The right hand side, there's a little bit more work to do there. So I get 2t plus 3t squared, but I'm going from 0 to t, so I will get 2t plus 3t squared. You can see, same answer, but a lot less working. By making it a definite integral, makes life a lot easier. So let's now solve the problem, and this is where it really becomes useful. Instead of calling velocity v, now I'm going to call it dx to t. I'm going to use the same idea, separate the variables. But notice here, yes, the bottom, I've gone when t is 0, x is 7. But at the top, I'm saying I want to know what x is when t equals 3. When I sub into this, it's going to give me the answer straight away. So let's integrate. And on the left-hand side, I couldn't just jump the x on this one, because now I'm going to have to put 7 in. So that's why I've made x and the limits are there. So subbing in, bingo. We get answer x equals 43 straight away. You don't forget the constant because it gets catered for in the definite integral. I just find it just so much more efficient solving these problems as a definite integral rather than an indefinite integral. I actually took this HSC one a long time ago now. But there's the function, x equals t minus 2 on t plus 2. What is the displacement when t equals 0? It's a bit of a gift for this first question. We just got to sub in t equals 0 and it's x equals -1. So thank you very much. Probably was only worth 1 mark, but we'll take it. Part 2. Now they're really giving us a hint. Show that x is that. Oh, okay. If I play algebraic fractions, let's put it all over t plus 2. What do you know? T minus 2 on t plus 2. They really are feeling generous this year. So there it is. We do know x is 1 minus 4 on t plus 2. Now, hence find the expressions for velocity and acceleration. Well, now I've just got to differentiate. So velocity, well, 1 differentiate 1, you get 0. And I'll use the reciprocal rule, minus the derivative on the function squared. And there's velocity. Differentiate it again to get acceleration. And we have our 2 expressions. Is the particle ever at rest? And this is the bit I know you're going to hate, but often they'll say, give reasons for your answer. Just explain how you know this. So give reasons. So what did I do? There's the velocity equation, and they're asking me, is it ever at rest? So they're asking me, can this fraction ever equal 0? And the answer is no, it can't equal 0. You got a fraction and a constant on the top of the fraction. We know that can never equal 0. So no, particle's never at rest. That cannot equal 0. What is the limiting velocity? So limiting velocity just means as time approaches infinity, what's happening to this particle? What's the limit that it goes to? So it's really just saying, what's the limit as t approaches infinity of the velocity? Well, the velocity was 4 on t plus 2 all squared. I want to sub in infinity. Well, I know the answer is 0. Remember, subbing in t equals infinity, you just look at the coefficients of the highest power. Now, okay, the bottom one's factorised, but if I was to expand it out, the highest power would be t squared. So I'm just looking for the coefficients of t squared. There is no t squared on the top of the fraction, so therefore 0 is on the top of the fraction. On the bottom of the fraction, I would have 1, 0 over 1. So the limit of that is 0, so that is our limiting velocity. Of course, another way you could do it, you could think of the graph. What is 4 on t plus 2 all squared? Well, it's a hyperbolic function. It would look something like that. And we can see from the graph, as t is approaching infinity, it's getting closer and closer to 0. We've got an asymptote there at the axis. So you might prefer to solve it that way. However you do it, there's our limiting velocity. It's 0 metres per second. Okay, what did they do the next year? Particle, again, straight line. Ooh, a trig function. X equals sine 2t plus 3. I think this was just a sneaky way of getting them to draw a trig graph. They made it look like a practical question. Sketch the graph. Oh, okay, we're going to sketch x equals sine 2t plus 3. Let's get our important information. The amplitude is 1. We've shifted the whole thing up 3. The period is pi. So on my graph, I'm going to mark my divisions off every pi on 4. So let's draw up our axes. There it is, marked off every pi on 4. But I'm shifting it up 3. I'm just going to dot in an axis there because I know my curve's going to wind around the x equals 3 there. Okay, sine curve. Normally we would start a sine curve at the origin, but this has been shifted up. So it's going to start at 3. What does a sine curve then do? It then goes up and down and up and down and up and down. And so there is our graph. X equals sine 2t plus 3. Using your graph or otherwise, find when the particle is at rest. When is the particle at rest? When the velocity equals 0. But that's where the graph is useful. What's the interpretation here of velocity equals 0? Velocity is the first derivative. Where are the stationary points? Much easier to use the graph for this one because you can clearly see all the stationary points. We know that it's going to be, the first one was when x equals 4. Then we've got x equals 2, x equals 4, x equals 2. Because it's going backwards and forwards, backwards and forwards. We're interested in the time though. So the time is pi on 4, then 3 pi on 4, 5 pi on 4, 7 pi on 4, and so on. And this is the bit you love. Describe the motion completely. This is where you get to be a little bit creative. What did I say? Did I use any big words? Oh, look at that one. Oscillates. That's a good one. So the particle oscillates between x equals 2 and x equals 4 with a period of pi seconds. Alrighty. That'll do us for today, eh?